we will study about the energy, especially mechanical energy. What is energy? Energy is the capacity to do the work. Units of energy are joule. Okay. Generally, you may be wondering why I am saying the joule. In general, we measure the energy in calories, but I'm saying that energy is measured in joules. Okay. But mechanical energy is measured in joules, whereas the thermal energy we measure in calories. And because the unit is a small one, joule is smaller than the calorie by 4.2 times. Okay. So we measure mechanical energy by joules and then thermal energy by calories. And then 1 calorie is equal to 4.184 joules. And this is called the mechanical equivalent of energy. Okay. And then today we are going to study about the mechanical energy under the mechanical energy, kinetic energy, and potential energy. Again, under the kinetic energy, we are going to study about the translational kinetic energy and rotational kinetic energy. Under the potential energy, we are going to study about the gravitational potential energy and elastic potential energy. Okay. Now, I told you that energy is the capacity to do the work. See, let us see how the energy and work are interrelated. That we study through the work energy theorem. What work energy theorem states? Work can be, if suppose work is done on the system, then that work can be stored in the form of energy. Suppose work is done by the system, then the stored energy can be expended. Okay, how it will be? Let us see through the mathematical form. Okay, we know what then is equal to force into displacement, or F dot D. And we know F is the force. Force is equal to ma, mass times acceleration. And acceleration is the change in velocity over a period of time. And then the displacement is the velocity times t. But here I am taking the average velocity. Okay. So Vf plus Vi by 2 is the average velocity times t. Okay. I substitute this mass, whatever the mass, and mass times acceleration and displacement in this equation. W is equal to Fd. No? In this, I will write mass times acceleration times displacement in terms of velocity and the time. Okay, so that I can get the another. I'm just this is mathematical jumbling. That's all. Nothing beyond that equation transformation. Okay, so W is equal to half m. This is a minus b times a plus b form. Okay, therefore a square minus b square. Okay, time cancels out, and then this is equal to half m vf square minus va square. So W is equal to half m vf square minus half m vi square. Half m vf square is called the kf, and then half m vi square is called ki. So the work done is equal to kf minus ki, or work done is equal to delta k, or change in kinetic energy. Or in general, we take work done is equal to change in energy. Okay. Now, suppose if it is the work done is equal to change in energy, then the change depends more on the initial value of the velocity and final value of the velocity, because the mass remains the constant, and then we can't change the mass. So the velocity changes, and then the velocity changes mainly depend on the kinetic energy change in increase or decrease in kinetic energy mainly depends on the initial velocity and the final velocity. Okay, here, especially if you see this one, the kinetic energy is dependent as the square of the velocity. Okay, so there is a small increase in velocity that manifests in the more kinetic energy because it is the square of the velocity. Okay, now how it will be, let us see through a mathematical problem. A numerical problem. The problem states that here, compare the increase in a 1000 kg cart's kinetic energy as it speeds up by 5 meters per second, starting from 5 meters per second, to its increase in kinetic energy as it speeds up by 5 meters per second, starting from 10 meters per second. Here, two parts. The problem is of two parts. Part one, the initial velocity is 5 meters per second and the increment is 5 meters per second. So the final velocity is 10 meters per second. So mass is 1000 kilograms, velocity is 5 meters per second, and then final velocity is 10 meters per second. Therefore, the change in kinetic energy is half mvf square minus half mvi square. So that is equal to half, m is 1000, and then velocity value I inputted, and then final velocity and initial velocity. And then on calculation, I'm getting 37.5 kilojoules. Okay. And then suppose in the second case, if I input the values of the values, the first one, initial velocity is 10 meters per second, and then increment is 5 meters per second. So the change in kinetic energy or increase in kinetic energy is 15 minus 15 square minus here 15 square is the final velocity, and 15 is the final velocity, and 10 is the initial velocity. And input the values in the equation, and you are going to get change in or increase in kinetic energy or change in kinetic energy 62.5 kilojoules. So that means you are seeing the difference. The increment is same, increment in the velocity is same, but the initial velocity and final velocity values are different. That is why the increase in kinetic energy or change in kinetic energy is different. There is a lot of difference between the change. Okay, so suppose if we represent the velocity, kinetic energy versus velocity graph, it will be a curve, not the linear one. Okay. Here you see, lower the velocity values, lower the change in, I can say that the change in kinetic energy is less. Higher the velocity, the change in kinetic energy is more. Okay. So in total, what I mean to say is that kinetic energy is the energy possessed by a body by virtue of its motion. Okay. So suppose if a body is moving with an initial velocity of 2 meters per second, suppose if you apply a force in the same direction of the motion of the object, then the velocity increases. As the velocity increases, the kinetic energy increases, but in a rapid way. That is what I mean to say through this. Okay. So here the work is done on the object, and that is manifesting in the form of increase in the velocity. Okay. So let us see how the work energy theorem and then energy changes. And before going into the details, I would like to say about this one. What is the system and surroundings? Whatever the objects under consideration are called the system, and everything else is called the surroundings, system and surroundings. Because here I am going to talk about the energy exchanges. Suppose work is done on the system, then the energy is transferred from the environment to the system. Suppose work is done by the system, then the energy transfers from the system to the environment or the surroundings. Therefore, the system is the one which all the objects we are considering is called the system. It may be one object, two objects, or n number of objects, but all the objects under study are called system, and then everything else is called the surroundings. That is one thing you should remember. And second thing is the internal forces and external forces. The forces between the objects within the system are called the internal forces. They cause the energy transformations within the system, but the total energy of the system remains constant. Okay. Suppose, for example, I will show you here. The person is pushing the shot or throwing the shot put. Okay, what he is doing, he is giving a swing to the shot and then throwing the shot. So here he is doing the work on the shot, and then that work is manifest in the form of kinetic energy. So work is done on the system by the environment or by the surroundings. So energy is transferred from the surroundings to the system. Okay. Now here you see another example where the boy is pulling the this one elastic band of the slingshot. This is the slingshot, and then he is pulling the band's backside, okay, pulling back. So the work is done on the system. The system is here, the slingshot, okay. So the work is done on the system. That is why the energy is transferred from the environment to the system, okay. Now, one more general example I will give. Striking a match to the matchbox. So here, what we are considering, the match and matchbox are the system, and then the hand which strikes the match to the matchbox is the external one. Okay, the surroundings or the environment. So the work is done on the system. So the whatever the work is done, that gets transformed into the thermal energy. Okay, so work is done on the system. That means the energy is transferred from the environment or the surroundings to the system. Okay, that you should know. That is the main purpose of this discussion. Okay, and then next I'm saying that the internal forces and external forces. What are the internal, or what are the either it is the work or whatever it may be, the internal forces it does, that remains within the system. Okay, so we are taking the isolated systems. What are these are called isolated systems. What are the isolated system is, you're considering all the objects in the system. Here the work and energy changes takes place within the system, not outside the system. So in an isolated system, the energy changes. If you work is done on some object here, for example, if you see this one, the object is freely falling. That means the object falls because of the gravitational pull. Okay, the gravity is the force acting on the object. Because of that, the object is falling down. But here I am taking Earth and the falling object as the isolated system. Okay, as one system. That is why what all the energy changes, what energy transformations are taking place, or the energy changes are taking place are within the system, and then the forces are internal forces, not the outside forces. So the work done by the internal forces manifests in the form of energy, and then the energy changes, what all that takes place remains constant within the system. Okay, so there won't be any energy transfer between the system and the surroundings, because you should know that the entire thing I am considering as the system. Okay, Earth I am taking as the system, Earth and the falling object as the system. That is why there is no environment outside this one. So what all the energy transformations are taking place are remains within the system, and then therefore the energy remains constant. Okay. Next, here, if you see this one, the object is sliding down a frictionless ramp. Okay, not frictional, frictionless ramp. So when it is the frictionless ramp, remember the frictional forces are the non-conservative forces. Now it is another concept I will explain after this one. What are the conservative forces and non-conservative forces? There are two types of forces: conservative forces and non-conservative forces. The work done by the conservative forces can be stored. Energy transformation takes place, but it can be stored in that. Suppose work done by the, for example, take the gravity and then the elastic force are considered as the conservative forces, and then friction is considered as the non-conservative force. Friction and then air resistance, air drag, these are considered as the non-conservative forces. So what is the difference between these conservative forces and non-conservative forces? The conservative forces take only the initial position and the final position. They will not consider the actual path traversed by the body. Okay, that means they consider the displacement, not the distance. Okay, conservative forces. So the work done by the conservative forces can be stored, or work done by the conservative forces is stored in the object, and then it can be used later. Okay. But whereas the work done by the non-conservative forces, for example, friction, what happens if you take the friction, if you take the work done by the friction, the energy gets transformed into thermal energy. The mechanical energy gets transformed into thermal energy. So the energy will not be conserved or cannot be stored. Immediately it is transforming into other form of energy. Okay, instead of mechanical energy, it is getting transformed into thermal energy. That is the thing. Okay, and one more thing is, suppose if you take the work done by the conservative forces in a closed system is equal to 0, because the displacement becomes 0. For example, if you take the roller coaster ride here, this is the starting point. It is going down and up and down and up and down like this. It is going, but finally it is reaching the starting point. So the displacement is equal to 0. That means it is a closed path. So the work done by the conservative forces in a closed path is equal to 0. Okay. Similarly, if you take here, the work done by the applied force and friction both is non-conservative, because here it is we are taking the path into consideration, whether it is point 1 to point 2, either straight line path or the semicircular path. Okay, what is happening here? We are considering the path into consideration. Suppose if we will not take the path into consideration, for example, gravity will never take the path into consideration. I will show you with an example here. Suppose here the work done by the gravity, for the person is climbing the hill. There are two different paths, path A and path B. When he takes the path A, it is a roundabout path. Okay, so the work done by the friction is a non-conservative energy. So the force is, the frictional force is a non-conservative force because it is considering the path. But whereas the gravity, work done by the gravity, here the length of the object, the length of the hill is, we are considering this is like this. How much it is? It is 200 meters. Okay. So here he is going in this path or in this path, whatever may be the path, but we are considering the height or elevation from the reference point. From the reference point, the elevation is 200 meters. So the work done by the gravity is conserved. Okay, so the gravity is a conservative force, and then it is, but the friction is not conserved. Immediately it gets transformed into the thermal energy. Okay, so this you should know. This is an important concept you should know before knowing into the work energy transformation. Okay. Now here again, an object sliding down a frictionless ramp. So the friction, we are not considering the friction, it is the frictionless. So, and earth and the object and the ramp are considered as the one system. That is why all the forces are internal forces. So the work done by the internal forces converted into energy, but the energy of the system remains constant. Therefore, the energy will not go out of the system, or energy will not come into the system, or the external forces. Those forces are not doing any work on the system. Okay. And then the next one is an object compressing a spring. Object is compressing a spring means what is happening here? Here again we are considering the earth and the spring mass as the one system. So here all are internal forces. So again the work done by the internal forces remains converted into energy. The system of the energy of the system remains constant. Okay. Here the object is sliding along a surface with friction. So what is happening here? Again, here the kinetic friction does the work, but it is within the system. That is why there won't be any transformation of energy. Okay. Here the block, the earth, and are considered as the single system. So the internal forces, the kinetic friction will also comes under the internal force. So everything will be internal. So there won't be any energy transfer between the system and surroundings. Okay. Now let us see how the energy transformations will be considered. We know that whenever the work is done on an object, whenever work is done on an object, that energy transfer takes place from the surroundings to the system. Here work is done on the object. When the work is done on the object, the energy is transferred from the environment to the system. So here what is happening? The work is done, okay, on the object. So a force is applied on the object, and then because of the application of the force, the object gets displaced, and then the angle between the force and displacement is 0. Okay, and moreover, the object is moving towards right. So the force and displacement are along the same direction, and then angle between the force and displacement is 0. So the maximum energy is transferred from the surroundings or the environment to the system. Okay, that is the meaning of this one. And then the sign is positive, means transferring the energies gets transferred from environment to the system. And if you take here, there is an angle between the force and displacement, but which is less than 90 degrees. That indicates that there is a transfer of energy from the environment to the system, but it is a bit less than the previous case. Okay. And in the third case, the force and displacement are perpendicular to each other. That means the applied force and the displacement are perpendicular to each other. That indicates that there is no transfer of energy. Okay. And then the next one here, the angle between the object force and the displacement is greater than 90, or in the last case, it is 180 degrees. That means the work done is negative. Okay, negative work done means there is a decrease in energy transfer, and moreover, the energy is transferred out of the system. In first two cases, the energy is transferred into the system. In these two cases, the energy is transferred out of the system. Okay, so internal energy is expended or something will happen. So energy is transferred from the system to the surroundings. That you should know. That is the beauty of the work energy theorem. Okay. Now, so far we have studied about the translational kinetic energy. Okay. Now let us study about the rotational kinetic energy. Okay. Now, what is the rotational kinetic energy? Rotational kinetic energy, just I will write here. Okay. I write about the rotational kinetic energy. K rotation is equal to half I omega square, where I is the rotational inertia or moment of inertia, and then omega is the angular velocity. How I arrive at this one, I will let you know. You know, K translational is equal to half mv square. Okay, and you know V is equal to R omega, where V is the linear velocity, and then R is the distance between the axis of rotation and the object. Distance between, or position vector, distance between the axis of rotation and the mass. Okay, and then here omega is the angular velocity. Okay, now I will write, I will input these values here. Okay, K is equal to K translational is equal to half m into R omega square. So that is equal to half m R square omega square. Okay, and m R square is the I, what is called, that is called the moment of inertia. rotational inertia. Okay, so half into I omega square is equal to K rotational. Okay, in general, what happens? We come across a mixture of kinetic energies. Both the objects will have both the translational kinetic energy and the rotational kinetic energy. Okay, so this is about the rotational kinetic energy. Now moving on to the next point, the potential energy. What is the potential energy? Potential energy is the energy possessed by a body by virtue of its position or configuration. Okay, now how it will be, let us see. Here, see, the book is on the earth initially, and then it is lifted from the ground to a certain height. Okay, and here I am considering the earth and the book as the system, and then hand as the surrounding. Okay, external object, external to the surroundings system. Now, what has happened here when the hand is lifting the object? So the force, external force is acting on the system. Because of the external force, work is done on the system. And then this work, and moreover, I am considering a frictionless surface. Okay. And then the object is moved with constant velocity so that there won't be any increase in the kinetic energy. And then as the system is friction free, that is why there are no dissipative forces, no conservative forces are acting on the system. So no non-conservative forces are acting on the system. So the work done by the non-conservative forces is equal to 0. So only the work done by the conservative forces comes into picture because the hand is outside the system. So work done on the system comes into picture because of the work done on by the external force on the system, and that too by the conservative force. It manifests in the form of energy, that is gravitational potential energy. And moreover here, what is happening? The work is done against the gravity. Okay, so the energy is stored in the form of potential energy. Okay, because because of the configuration. Okay, here the state of the object has been changed from the ground to a certain height. It has been moved from ground to a height. Now let us see how it will be. W is equal to F dot D. And then here the force is nothing but its own weight mg. And then the displacement is a height. Therefore, W is equal to mgh. Mgh is the UG, or we call it as the gravitational potential energy. Okay. Now, there is another type of energy that is called the elastic potential energy. Okay. Now, what is the elastic potential energy? Before studying the elastic potential energy, you should know about the Hooke's law. Okay. What is Hooke's law? No, whenever a force acts on a system, it changes its shape. The force has the ability to change the shape of an object. For example, this is a sponge. Okay. When it is squeezed, what is happening here? It gets compressed. So the shape of the sponge has been changed. Okay. So if it happens within the elastic limits, then the internal forces will try to bring the object's shape back to its original shape. Okay. So those forces are called the restoring forces or restoring forces. Okay. So the restoring forces always act in a direction opposite to the compression or elongation. Here I give one more example. See the spring here. Here, this is the unstretched spring. So compression or stretching is 0. Okay. Next, what I am doing, I am pulling the spring a bit more. Okay. So by the application of the force, the spring has been stretched by an amount x. Now what happens? The external force is acting in this direction. Both the external force and the displacement are stretch are in the same direction, whereas the restoring force acts in the opposite direction to the displacement or the stretch. So that is what I wrote here. The restoring force and the stretch are opposite and are proportional to each other. Okay. Similarly, in the next case, what I am doing is the applied force is compressing the spring. When the applied force is compressing the spring, the restoring force is tries to bring the spring back to its original position. Here again, the compression and the restoring force are oppositely directed. So that is what I represented. It is nothing but an empirical formula given by the scientist Robert Hooke, and this is called the Hooke's law. So F restoring is directly proportional to the displacement, but the restoring force and the displacement or the compression or elongation are oppositely directed. Okay. So the same thing I wrote. Here the K is called, then we have to equate this one to remove the proportionality constant. I have to introduce a constant that is called the K. K is called the spring stiffness constant, or in general we call it as the force constant, and then the units of the force constant are Newton per meter. The negative sign is just indicating the restoring force and displacement are oppositely directed, nothing beyond that. Now coming to the elastic potential energy. Here, what happens? Initially, the spring is in the equilibrium position or rest position. That means there is no elongation or compression. Now, what I am doing is by keeping the ball, I'm just compressing the spring. That means work is done on the spring. The moment the external force is removed, the object, that means the spring, does the work on the ball, and then the ball is kicked out. Okay, this is what is the elastic potential energy that I will represent mathematically. Work done is equal to force dot displacement, and then here the force, initially no force is acting on it, that is why it is 0, and then later the force is applied, and therefore F final is equal to kx. That is why I have to take the average. One is 0, another one is kx, so I have to take the average. So F average is equal to 0 plus kx by 2, or I can write it as half kx. Okay, and then displacement is nothing but x. So work done is equal to force into displacement. So W is equal to half kx into x, that is called half kx square. This half kx square is called the elastic potential energy. Okay, this is about the elastic potential energy. So today I have discussed the kinetic energy, and then the potential energy, and then in the kinetic energy, translational kinetic energy, and the rotational kinetic energy, and in potential energy, gravitational potential energy, and elastic potential energy. Okay, and then there is one more concept called the conservation of energy. That also I already discussed it so far, but again I will tell you. So the law of conservation of energy. Law of conservation of energy is nothing but law of conservation of energy. This is the last topic in the energy. Law of conservation of energy states that in an isolated system, the total energy of the system remains constant. Okay. So I already discussed about the isolated system, and then the energy changes. Unless otherwise an external force acts on a system, the total energy of what all the work energy transformations are taking place remains constant. So the total energy of the system remains constant. That is what is called the law of conservation of energy. Generally, people will say that energy can neither be created nor destroyed, something. Okay. So here, in an isolated system, the total energy of the system remains constant. No energy transformation takes place between the system and surroundings. I already discussed about the system and surroundings. No, what all the objects you are considering under the for the study are called the system, and then the remaining things, what all remaining outside, are called the surroundings. Okay, just whatever you are considering for the study are the system. Remaining ones are called the surroundings. So in an isolated system, the total energy of the system remains constant. That is what is called the law of conservation of energy. That means, suppose if there is a potential energy, that potential energy gets converted into kinetic energy. And then if there is a kinetic energy, the kinetic energy gets converted into potential energy. Like this, the energy transformations will take place within the system, and then the total energy of the system remains constant. Hope this helps. Thank you. Bye bye.